Okay. Okay, David and Brooks say that the audio is good, so um, I guess we're ready to go here. Um, I apologize on behalf of Zoom for the late start. The Zoom system is not my very favorite by any stretch of the imagination. Okay, let's see. We want to start from the beginning. Okay, I think, okay, I assume that you can hear me on the audio. If you can't, send me a message in the chat box or just speak up on the audio stream. So this is Paul Guyer, and welcome to this PDH Source webinar, an introduction to noise control in buildings. Just a brief introductory note. Normally the way these webinars move forward is I press on with the presentation for 50 minutes, then take a 10-minute break, 50 minutes, 10 minutes, keep running through that cycle. Now, since we got a late and awkward start today, I'm going to skip the 10-minute break and we'll just run straight through the 2 hours. So that having been said, let me see if I can find my controls here and how I move my slides. Okay, there we go. Here is what I'll be talking about today. Oh, by the way, a further introductory comment. This is an interactive webinar, and so questions and comments are welcome and encouraged. And we have two ways of communicating. One is that you can just speak right up on the audio stream and I'll respond. The other is to use the little chat box and just type in your question or comment. So here's kind of the way I'll be running through this topic, kind of the chapters in the book, if you will, some introductory comments on acoustics, kind of the physics involved, fundamentals of acoustics, and then noise criteria. This is your target, what you are designing for in building design. And this webinar, is, I'm sure you probably already have been aware of, this is talking about acoustics in building design, noise control, providing an appropriate noise or sound environment for the occupants of the building. By the way, I use two words there, noise and sound. They're not exactly the same thing. Noise is a subset of sound. Noise is unwanted sound. So noise criteria, this is your target in the design of a building. And chapter 4, I'll talk about sound distribution indoors inside a building, because that's basically what we're talking about. I'll talk about sound isolation between rooms, because that's what you're doing with noise control in a building, is you're separating the noisy room, if you will, from the quiet room. And I'll tend to use the simplistic terms, the source room and the receiving room. The source room is the noisy room. The receiving room is the one where you want things to be quiet because of whatever human activity is going on in that room, sleeping, having a conference, listening to a musical performance, something like that. At chapter 6, I'll have a few brief comments on sound propagation outdoors. That is when the source room is, if you will, is outside the building. And you've got a freeway running by your building and it's noisy, and you want to manage that noise that does get into your building. Airborne sound control, we won't get into that. That is kind of what you do for the occupants of your building when you can't control the sound adequately with the features that you design into the building. And that's when you have to start using personal protective equipment, things like that, mufflers on engines and so on and so forth. Okay. By way of introduction, this is a little bit about me and what I've been doing to make a living for the last few decades. For 35 years, I was what I characterize as a straight ahead building designer, rather broadly based. Did a lot of building design, infrastructure design. I did not spend the last 35 years doing nothing but noise control and acoustics engineering. But it just so happened that as I went along, these projects just started coming in through the transom that involved noise control. And so that's kind of what I have been doing. And I got registered in a few different things along the way. I'm basically a mechanical engineer. That's my degree and my first registration. So that's me. Okay. The purpose of this course is to introduce you to the fundamentals of acoustics and their application in building design and urban development. There's far more information that is included on these PowerPoints than we'll be able to get to today in this presentation. But you can get a copy of these PowerPoints from PDH Source, and I would encourage you to do so. It's not, these PowerPoints are not a design manual or a technical discussion, detailed technical discussion, but they've got some good information there if you're just beginning to address these noise control issues in building design. And comment here about sound and noise. A companion with sound is vibrations. Both sound and vibrations begin and are generated when something starts vibrating. It could be a string on a violin. It could be the speaker in a stereo system. It could be machinery, fans in a fan room rotating and banging around and making noise. But along with sound, a companion is vibrations. And the distinction kind of is that sound is perceived by a human through the eardrum, whereas vibration is perceived through the fingers and toes. So as an example, a fan room in a building, common situation. The the sound, the source room, the mechanical room needs to be constructed in such a way and using appropriate materials and construction designs to isolate the sound or at least reduce it to an acceptable level so it doesn't disturb the occupants of the building who are outside of the mechanical room. But then there's also vibrations. And again, using the example of a fan room in a building, you've got a fan in there, it's rotating, it's bouncing up and down, and it's shaking the building, the columns and the beams and the deck plates and this sort of thing. And that is also something that has significant potential to annoy the occupants of the building. And so you need to address those vibration issues if that is appropriate in your design situation. So sound and vibration, they both they are generated by something that's vibrating, a violin string, vocal cords, people talking, machinery operating. And then there can also be vibration that is produced and transmitted throughout the building. The sound is primarily, and sound and noise is primarily a through the air phenomena. Vibration is transmitted through the solid members or elements in the building, the columns, the beams, the decks, etc., etc. Okay, now in addressing sound and noise, there are some principles or aspects of the physics of sound that are important. And the best way to visualize them is picture in your mind a sinusoidal curve bouncing up and down, up and down, up and down, up and down, up and down. Now that sinusoidal curve then, it has one characteristic of it is level or magnitude. The curve may go way up high and then drop down way low and then back up way high, back down to low, or maybe it doesn't have, the curve does not have that large up and down characteristic. It's just a little teeny one, up, 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 down, up, down, up, down, up, down. And this is a measure of the intensity of the acoustical energy or the loudness. So if the acoustic curve, the acoustic energy curve, if you will, has a large magnitude, that's a loud sound. If it just has a little teeny sound, that is a quiet sound. So level or magnitude is an important characteristic of sound that you need to be cognizant of and address it as appropriate. A second major characteristic of sound is frequency and spectral content. In other words, again, going back to the sinusoidal curve, up, down, up, down, up, down. If that is is a very fast frequency, up, down, up, down, up, down, up, down, up, down, that is a high-pitched sound. And this is important in talking about noise control, because the human ear is only sensitive to in a kind of a fairly fixed range of frequencies. If the sound is, the frequency is too high, that's outside the range of the human ear, and the human ear just doesn't hear it. Similarly, if it is a very a slow up, down, that is a quiet sound, and it may be outside the range of the human ear to perceive. I think we all know that, as an example, dogs have a much broader, significantly broader span of frequencies of sounds that they can hear, are sensitive to. And that's why your dog's sitting there in the living room and you don't hear anything, but your dog starts barking because it hears something outside. So frequency is an important dimension of sound. And then spectral content, because in the real world, you practically never hear a sound with a pure level or magnitude and a pure frequency. What you hear is a bundle of sounds all at the same time. Like right now, when I'm talking, you're hearing sound at different levels and at different frequencies as I speak and move along in what I'm saying. Um, and the spectral content is an important characteristic to keep in mind when you're hearing a sound in the real world. You're not hearing a sound with a pure level or magnitude and with a pure frequency. You're hearing a bundle of sounds with different magnitudes and different frequencies. And then the third concept to keep in mind is that of time or temporal variations. That is, that the sound, as you move, as you're hearing it at this instant in time, you move just a tiny bit forward in time, and you're actually hearing something different. And this is what allows us, as an example, to have to speak. And the brain and the vocal cords have a phenomenal ability to control the magnitude and the frequency of the sound that you are producing from moment to moment. So that's important to keep in mind. Okay, all very interesting. Now, sound, what are you talking about? Well, you have to measure sound, and you may already have come across this standardized way of defining the level of acoustics, and that is the unit is the decibel, which is abbreviated dB. And the definition of a decibel, how you calculate it, if you will, is you would use equation 2-1. Decibel equal 10 times the log of parenthesis log P1 divided by P2, close parenthesis. Now, P1, the way you perceive sound is pressure on your eardrum. Because that's what you're doing when you make noise. You're changing the pressure. You're creating pressure in the through the air in the environment. And P1 in this equation is the sound pressure actually being perceived by the eardrum of the receiver. It's pushing on the receiver's eardrum. P2 is a reference sound pressure. And what it is, and this has been established in the uh, uh, engineering of acoustic systems over many decades. P2 is that sound pressure which can just barely be perceived by the young human ear. In other words, it's a very quiet, barely audible sound. And so this P1 over P2 is the ratio of your actual sound pressure impinging on the eardrum divided by the reference sound pressure, which is that which has been established as a standard to represent the sound that is just barely perceivable by the young human ear. And the sound pressure is that reference sound pressure is about, for the young healthy human ear, is around 20 decibels. Now, you might say, okay, that's very interesting. Suppose, as an example, I have two sources of sound in a source room, the noisy room, and they are producing sounds of different decibel levels, and I want to add them together so that I can characterize what I or a receiver, a human receiver, would actually be perceiving. Well, you can go through the arithmetic and calculate the sum of adding 2 decibels together. But let me tell you right up front that in building design, this is something that you're almost never going to have to worry about, adding decibel levels together. Now, to give you a hands-on or kind of a physical feel of what happens when two different sources that are producing sounds at different decibel levels, this table here gives you a little feel for how this works in the real world. If the 2 decibel values being produced they differ by between 0 and 1 decibels, the sum of them will be approximately 3 decibels higher than the higher of the 2 decibel levels. If you've got 2 decibel sources that are producing sounds that differ by between 2 and 3 decibels, then the sum of those two that is perceived by the receiver is about 2 decibels, and so on. If the 2 decibel sources differ by 4 to 9 decibels, then the sum of them will be perceived at about 1 decibel higher than the higher of the 2 decibel sources. And if the 2 decibel sources differ by more than 10 decibels, the sound that will be perceived is not any higher. There's 0 decibels added to the higher of the 2 source decibels. And this seems counterintuitive, but it isn't, because what's happening is as your 2 source sounds are farther apart, one of them low, one of them high, the higher of the 2 decibel level sources is just going to, as far as the human ear is concerned, is just going to overpower the lesser of the 2 source decibel levels, and that's why if the two sources differ by 10 decibels, the sum that you're going to hear is going to be the same as the highest of the two source decibel levels. If you for any reason wanted to go through and do the arithmetic, you could do so using equation 2-2. The sound level, the sum of the sound levels is 10 times the log of the quantity in parentheses there, and you just plug in your different source sound power levels and do the arithmetic, and that gives you a calculated sum of the sound power levels of the different sources. But again, as far as building design is concerned, don't get too caught up in this, because you're almost never going to have occasion to do that, to have to do that. Equation 2-2 can be reduced if all of the source sounds are of the same decibel level, and you want to know what the sound will be if you sum all of them. Equation 2-2 reduces to equation 2-3. So that's that. Also, again, in the category of don't worry about it, because in building design, you're probably never going to have occasion to want to do it. But if you wanted to subtract 1 decibel level from another, as far from two different sources, you could do that using equation 2 for the perceived sound by the human ear would be L diff equals 10 times the log of the quantity that you see there. And if you should ever want to take an average of several sound sources that are different, you would use equation 2-5. Okay, sound pressure levels. So what causes the human ear and the human brain to perceive sound is pressure on the eardrum. And that is in calculation form, usually abbreviated L sub P, and in text form is usually written SPL. The sound pressure level in decibels, we saw this equation earlier. It's 10 times the log of P over P reference, that being the sound pressure barely perceivable by a young healthy human ear squared, and equation 2-6 can also be written as equation 2-7. Again, as I keep saying, don't worry about it. It's probably not going to be something you're going to run into with building design. So now this reference sound pressure, the one barely perceivable by the young, healthy human ear. What is it? Well, it's been established by just observing nature over many decades and centuries, perhaps. The young, healthy human ear just barely perceives a sound of 20 micropascals. And that obviously there can be differences with different human ears, but that's the standard or the reference that has been established. So 20 micropascal sound pressure is 0 decibels. And in the strictest sense, a sound pressure level would be stated completely as an example as 85 decibels relative to 20 micropascals. But we don't bother doing that because the 20 micropascal um, uh, reference pressure is so well known and recognized. Okay, now sound power level is the measure of the quantity of acoustic energy produced by a sound source. It's defined by the equation 2.8. The sound power is equal to 10 times the log of the sound power being perceived divided by a reference sound power. Again, that is the sound power that is just barely perceivable by the young, healthy human ear. And that is 10 to the minus 12 watts. And that's the sound power that is barely perceivable by the young, healthy human ear. Sound power level is usually abbreviated PWL, and in formulas and notations as L sub W. A point to keep in mind is that sound power level is not something that you can go into the field and measure. And the reason is you visualize a point source of sound, and it's emitting, if you will, these sound vectors in essentially kind of an infinite array of vectors in different directions in a three-dimensional 360-degree configuration. The sound is being propagated outwards, and the only way you could measure in the field, if you will, the sound power being produced by a source is if you could measure all of those sound vectors and add them up and get the total sound power being produced. But it's not practicable to do that. Nobody's invented a sound power meter that could do that, and there's really no need for that characteristic. Okay, now I'm, as you see, I'm kind of, as I pointed out, I think at the start, I'm kind of speeding through these slides because there's much more information here than we can address today. Sound intensity level. Sound intensity is the sound power per unit area. The sound is waves, if you will, is impinging on a wall between a source room and a receiving room. And the sound intensity is the sound power per unit area of whatever area you are dealing with. the area of a wall between two rooms, as an example. So the definition of sound intensity level is given by equation 2.9. L sub I, sound intensity level, is equal to 10 times the log of I, the sound intensity perceived, divided by I ref, which is a reference sound intensity. And that is the sound intensity, just barely perceivable by the young human healthy ear, and it's in watts per square meter. And the base, the reference intensity is 10 to the minus 12 watts per meter squared. There's a typo in that first paragraph on this site. That should be 10 to the minus 12, not 10-12. Calculation of the sound power level from the intensity level. You can do that using equation 2.10. Again, like so much of the stuff, as far as building design is concerned, you're practically never going to have to deal with it. Okay, now let's talk very briefly about vibrations. And just to illustrate how vibrations is a fellow traveler or analogous to sound. The definition of vibration level is given by equation 2.13. L sub A is equal to 10 times the log of the quantity that you see inside the parentheses. And what the one thing that is an important thing to keep in mind as far as vibrations is concerned, when you have a source like a fan room in a building, and that is that, let's get to, okay, actually, we'll get to what I was going to say about vibrations. We'll get to that a little bit later. The one thing to be aware of in building design as far as vibration is concerned is resonance. Every mechanical or structural system in the real world has what is called its natural frequency. And if you impose a force on that system at a certain frequency, if you impose that force at a frequency which is at or very close to the natural frequency of the mechanical or structural system that you're talking about, the building, then resonance is induced, and the target that you're forcing is it's the amplitude of its vibrations, up and down, and so on and so forth, increases until if you continue applying that forcing frequency to the system at or near the resonant frequency of the system, pretty soon the amplitude of oscillation gets so high that the system breaks. The beam fails, and obvious. So you want to stay away from that natural frequency, and it's extremely difficult to try to calculate the natural frequency of any mechanical or structural system. It's largely something that has to be determined or estimated based by laboratory and field tests. Now, moving on and looking at frequency of the sound that is produced. The sinusoidal curve, again, up and down, up and down, up and down real fast. That's a high-pitched squeaky sound. If it's slowly oscillating up and down, that's a very bass type of a sound. The frequencies for primarily for the convenience, if you will, of musicians and folks like that. The frequency of the sound has been divided by the profession and the industry, just because that's the way it is, into what are called octaves. And so this table here gives you a picture of the octave bands of sound. The lowest octave band of sound is the one at the top of this table. The lowest part of this band of frequencies is 11 cycles per second. The upper band is 22 cycles per second, or hertz. 1 cycle per second is 1 hertz. And the center of this band is 16 hertz. And so that band, acoustic sound level band, is called the 16 octave. And you keep going through this table here until you get to the top, to the bottom, and you get to the highest frequency acoustic octave. The lowest limit is 11,360. The highest is 22,720. And the center of that octave band is 16,000 hertz. So this table is showing octaves from the 16 through 16,000. That's from a very low sound to a very high-pitched sound. And this represents the spectrum of frequencies that the human ear is sensitive to. So the human ear is sensitive to octaves from 16 hertz to 16,000 for reasons that, again, are more of interest to musicians and people doing things other than designing buildings. These octave bands have been divided into what's called 1/3 octave bands, which is simply taking a given octave band and chopping it up into 3 parts. And so this is a representation of the frequencies that are perceivable, again, by the young, healthy human ear. Okay, that's a little quick run through of the underlying physics. What's important is the magnitude of the sound being produced, the frequency of the sound being produced, and then taking into account the fact that you're at any given point in time hearing a sound. You're not hearing a pure sound with a single frequency and a single amplitude. You're hearing a whole bundle of sounds. Okay, now from the standpoint of building design, how do you approach the typical design project or feature? Well, step number one is to find out uh, what is the magnitude of the sound that is being produced in the source room. And again, I talk for simplification purposes about a source room in a building and a receiving room in a building. The source room is where the sound is being produced. That's the noisy room. The receiving room is where the human occupant is located, and that's the space where you're trying to uh, maintain an acoustic environment that is consistent with whatever the human occupant is doing, trying to sleep, uh, watching television, engaging in a business conference, that sort of thing. Well, so right at the start, you need to find out what is the sound level that is being produced in the source room. And you do that by measuring it with a sound level meter that looks kind of like what you see here. And they are they're a no, I don't want to call them a simple little instrument. But they're easy to use. And on the typical sound level meter, it's a handheld thing, and you go into the source room and you measure the sound that's being produced. And the sound level meter typically has two dials on it, or knobs. Um, one of them says ABC on it, and the other is the um, the frequency where you read the frequency. And so and the other knob is the fast slow knob. So you've got two knobs on the sound level meter, A, B, and C, and then fast and slow. Now the ABC knob uh, that controls some filters, sound filters, that filters out some sound. In a minute, you'll see a figure that illustrates these A, B, and C weightings. But the setting the knob, the ABC knob, to A, B, or C, you are filtering out um, a certain amount of the sound at certain frequencies that is being perceived. We'll talk more about that a little bit later on. The fast slow knob, this is controls the rate at which the sound level meter samples the sound. It if it might sample the sound at every 1 second, and so the needle on the meter shows a certain value, And then 1 second later, it may show a slightly different sound level. And you need to have this fast, slow knob because if you sample the sound with a high level of frequency, like once every 1/100th of a second, the needle on the sound level meter will be bouncing back and forth like crazy, and you won't be able to read the sound level meter. So uh, you set the sampling rate on using the fast slow knob, and generally speaking, for building design purposes and that sort of thing, you're going to set the fast slow setting on the slow setting, and on the slow setting, the sound level meter samples the sound about once every second. If you set it on the high level, uh, the sound level meter will sample the sound about every 1/8 of a second. And there may be some specialized situations where you would want to use that uh, fast sampling rate, but with typical, again, building design, you're going to set that knob on the slow setting. Okay, and now the other knob, the ABC knob, let's move forward. The best way to get an understanding of the filter, sound filters in the sound level meter is by looking at this figure 2.2. And you see three curves, A, B, and C. And the plot here is of the uh, frequency being perceived and the loudness, the decibels. So as an example, on the with the A curve for the A setting on the sound level meter, at say 250 hertz, you see that the sound level meter is going to filter out or ignore about 10% of the sound that is perceived. And so you can follow these three curves through the frequency spectrum perceivable by the human ear from roughly around 16 hertz up to 16,000 hertz. And what you see here is with the A setting on this ABC knob, that the sound level meter using these acoustic filters filters out quite a bit of the sound that it perceives below about 1,000 hertz. And then up above 8,000 hertz, it also begins to ignore a certain percentage of the sound being perceived. And then the B and C curves are what you see here. The point here, the important point is that the A setting is kind of a representation of the sensitivity of the human ear. And so below 1,000 hertz, the human ear doesn't perceive as much sound. And so the sound level meter on the A setting ignores or filters out amounts of the sound. and the lower the frequency, the more of the sound that is ignored by the sound level meter. And that's because that's the way the human ear performs. It uh, is sensitive primarily to the sound frequencies between about 1,000 and 8,000 hertz. And the B and C settings are ones that might be used in specialized situations, but generally speaking, you are going to want to take your sound level measurement readings with the ABC knob set at the A filter level. And then the the sampling rate, the fast slow knob, you'll set on the slow sampling rate, because on the fast sampling rate, the needle on the sound level meter is going to be unreadable. So that's what you're doing now. You're going in to the source room. You've got your sound level meter. You set it on the slow uh, A setting, and you read the sound level in the room. Now so there are two kinds of sampling that are going on here. One is the rate at which the sound level meter samples the sound. And then there is the frequency with which you, as the person taking the measurements, sample the meter. In other words, you go in and you look down at the sound level meter, and you see it says such and such decibels, and you write that down on your clipboard, and then you wait 15 seconds or 30 seconds or a minute, and then you look down at the meter and you read it again. You record that decibel level, and you keep doing this. So there's the meter sampling the sound and you sampling the meter. And you do this in accordance with some technical guidance that you have come across in the technical literature or in ASTM standards for taking sound level measurements. And this you sample, we'll say as an example, every 15 seconds you look down at the meter, record the sound level, you look up, wait another 15 seconds, look down, record the sound level that you see, and you do this for the period of time that is defined by the technical guidance that you are using. This may be an ASTM standard. It says when sampling freeway noise, this protocol is recommended. When sampling railroad noise, train noise, this is the protocol to use with that kind of sampling. So you end up, as far as your field work, your measurement of the sound in the source room, you end up with all of these field notes that you've made. You then combine those into a single number using a methodology that has been developed and used over the years. And this gives you a single number that is a representation of the sound environment being produced in the source room. And it obviously this is not exact, but it doesn't need to be exact in building design. This reducing the sound level to a single number is an accepted and practicable way to characterize the sound being produced in the source room. And that is, so that number might be 100 decibels. But you, in the receiving room where the humans are located, you want to reduce that decibel level so that it's consistent with whatever the human activity is that they've got going on. They're trying to sleep, they're listening to concert music, they are engaged in a business conference or whatever. And so you have a sound level in the source room. You want to reduce it to an acceptable level in the receiving room. And the way you reduce the sound is by constructing barriers, essentially. And the barriers are the things that we design into buildings: walls, ceilings, floors, things like that. Now, these slides I'm on now, the speed of sound and wavelength, we're not going to get into this. This comes into play when you're like designing mufflers for mechanical equipment, motorcycles, or different pieces of equipment like that. So let's, okay, now one other point to touch on is the concept of loudness. And loudness is a judgment call by a human being. In other words, a human being hears a certain sound at a certain decibel level. Does the human consider that sound as loud, medium, quiet, this sort of thing? And this is strictly a judgment call, and to illustrate how a human would characterize different sound levels is illustrated in this table too. You've got a sound that's being produced, and if you reduce it by 3 decibels, if you went through and did all the arithmetic, the acoustic energy loss is about 50%. The human would perceive that as a perceptible change in the sound level. If the sound level was reduced by 10 decibels, the acoustic energy loss would be about 90%, and a human would perceive that as about half as loud as it originally was. And on down through the table to if the source sound is reduced by 40 decibels, the human would perceive that sound as being about 1/16 as loud as it was initially. This table just gives you a little feel for how humans uh, perceive loudness. Okay, jumping back just for a minute here to vibrations. Let's see. Here is a picture that illustrates what I said is an important consideration in building design and in design of equipment of one sort or another. And this is this figure is a plot of, on the horizontal axis, the forcing frequency. Visualize, if you will, one of these old slinky toys you had when you were a kid, a spring, and you bounce it up and down with your hand. And the frequency of your hand bouncing up and down, that's the forcing frequency. The system, the mechanical system in this case, that you're applying the forcing frequency to is a mechanical spring. And if the natural frequency is, if you apply the forcing frequency at or near the natural frequency of the mechanical system that you are dealing with, then you get resonance. And so you visualize the slinky bouncing up and down. And if you apply your forcing frequency to it at its resonant frequency, the amplitude of the slinkies bouncing up and down increases and increases and increases until finally it would conceivably break. This table illustrates the the forcing frequency divided by the natural frequency plotted against the transmissibility or the amplitude of the oscillation of the mechanical system, of the beams and columns and so on and so forth in your building. And if the forcing frequency, the fan running in the fan room happens to be running at or very near the natural frequency of the building, the fan can set up resonant oscillations in the building structure, and in theory you end up with some kind of a destructive breakdown of the building structure. But this resonance is a very complex determining the resonant frequency of any mechanical or structural system is a very difficult thing to do. And so now, another interesting little point here, and this is one of those things that does come into play in building design. In building design, one of the common bugaboos is that fan room, where you've got a fan that is rotating at a certain speed, and that's a forcing frequency. And one of the ways that you typically try to deal with these vibrations produced by the fan is to you mount the fan on some resilient or mounting system. Now, this, in some cases, this might just be a thick neoprene pad. You mount the fan on the pad, and the pad provides enough isolation such that the resonant frequency of the building is not approached. Also, another common device that is used with fans and similar mechanical equipment is spring isolators. And these are little springs inside a housing, and you put 4 of them down on the floor slab, and then you set a base structure of some sort on top of these 4, or could be more, spring isolators. And then you set the fan on top of the support structure. And when the fan is running and vibrating, the spring isolators bounce up and down a little bit and isolate the building structure, the floor deck, the beams, and columns from the oscillations that are produced by the rotating fan. However, something you need to look out for is the forcing frequency being at or near the natural frequency of the spring mount that you have selected. And the the natural frequency of the amount of the isolator, the spring isolator, is given by equation 217, 3.13 times the square root of 1 divided by SD, or static deflection. In other words, when you, in an unloaded condition, the spring isolator is 2 inches long. And then when you put the fan on top of the spring isolators, the spring isolators squash down, or there is a static deflection. And so you would plug in what that static deflection is into equation 217. And that would tell you the natural frequency as an estimate, the natural frequency of the fan and spring combination. And if the fan is causing the springs to bounce up and down at close to the F sub n value calculated by equation 217, then there will be resonance induced in the fan spring system, and that could lead to some kind of a failure of the system. So what it is if you do the calculation indicated in equation 217, and it looks like your natural frequency of the spring isolator is going to be close to the forcing frequency imposed by the fan, then you need to just select a different spring isolator. This is just one of those little back of the envelope type things that you should do with a fan room. Okay, now let's continue to press on. This table, continuing to talk about resonance, just indicates that your objective is to isolate the building structure from the vibration induced by the fan rotating. And if the ratio of the forcing or driving frequency is the ratio of the driving frequency to the natural frequency of the spring mount. If it is less than 1.4, that's getting close to the natural frequency of the spring and fan system, and therefore you're getting dangerously close, you might say, to having a resonant frequency failure. And so on down through this this table, with the ratio being 1.4 to 3, there would be negligible vibration isolation provided, isolating the fan from the building structure. If the ratio of the driving frequency to the natural frequency is in the range of 3 to 6, you would have a low degree of vibration isolation, and so on down through the table until when you get a ratio of the driving frequency to the natural frequency of the mount above 10, then the that's where you're getting a high degree of vibration isolation or protection of your building structure from the vibrating fan. Okay. All right. That's kind of a quick walk through some of the high points of the physics of noise, sound, and vibrations. Now let's look at noise criteria, which is the your target in building design. There are two quantities that have been developed. One called the room criteria and the other called the noise criteria, RC and NC. Of these two, in building design, the noise criteria, NC, is the one that you are going to probably use in most real world building design situations. A third quantity is called the speech interference level. This is intended to address the issue that in a receiving room, if you've got two humans there and they need to communicate to each other, then you need to keep the speech interference level low enough to an acceptable level so that two people in the receiving room can talk to each other. Let's get a picture of this important criteria, the target in building design. And the target is characterized by what are called these noise criterion. And these are curves which, when plotted of frequency to sound pressure level, they look like what you see here. Sound pressure level on the vertical, well, actually the horizontal axis is from 0 to 90 in this illustration. And that's because these are the sound pressure levels that can usually be addressed through the design of the building, the walls, the ceiling, the floors, etc. You get above about 80 decibels, and that's where prolonged exposure of a human ear to that loud a noise, there's a high level of risk of permanent hearing damage. And when that kind of an environment exists, you've got to go to personal protective equipment like earmuffs and things like that. And this is like you see at the airport, the workers that are working around the aircraft are typically they're wearing earmuffs, and that's because the sound environment is quite high around something like jet aircraft. And then this table here that or chart that characterizes the noise criteria curves between the frequencies of around 63 hertz up to 8,000 hertz. This is the part of the frequency spectrum where the human ear is particularly sensitive to loud noises. Now, so let's back up just a little bit and make sure I got that point across. So you've got these different curves here, NC15 through NC70. And an NC15 curve is the one down at the bottom, the black one. And the NC70 curve is the one up at the top. So a quiet environment would be represented by the NC15 curve down at the bottom. A noisy environment would be represented by the NC70 curve up at the top. And what you do in designing your structure is you select the NC curve that you want for people, occupants in your building to be exposed to. So it these NC curves 15 through 70, they relate to the human activity that's going on in the receiving room. And here is, whoops, I've been going backwards here. Stick with me for a minute while I get my, okay. So what your NC curve is your target in building design. You want to construct your building such that in the receiving room, the quiet room, you have an NC such and such environment. So how do you relate these NC curves to human activities in a building? Well, this is one approach to it. It's one that is has been used for many decades by most experienced building design and construction enterprise in the US and perhaps the world. And that's the military facilities in the United States, the Army Corps of Engineers and the Naval Facilities Engineering Command. And they have developed over the decades this guidance table here to assist the building designer in selecting the noise environment that is acceptable for the human activity that's going on in different kinds of spaces in a building. So category 1 up at the top, these are rooms, sleeping spaces, hospitals, etc., residences, apartments. And for those types of spaces, this system recommends an NC 20 to 30 noise environment. Category 2 allows a little bit noisier environment. This would be in spaces like auditoriums, theaters, conference rooms, so on and so forth, where you're what you're concerned with is to have good listening conditions. And in this category 2, the NC recommendations are for NC 15 to 30. Category 3, a little bit noisier environment is acceptable, but you still want to have good listening conditions. And this would be potentially your target for private offices, small conference rooms, classrooms, etc. And in category 3, the NC recommendation is 30 to 35, a little noisier. Moving down the table, category 4 is larger offices, reception areas, shops, stores. You want to have fair listening conditions. And so you would select as your target an NC 35 to 40 NC environment. Category 5, well, noisier environment is acceptable. Lobbies, laboratories, maintenance shops, you would select an NC 40 to 50 target for those spaces in your building. And then category 6, the noisiest spaces in a building, kitchens, laundries, shops, power plants, so on and so forth. And in those spaces, you would select an NC target value of 45 to 60. And this then tells you what you want the noise environment to be in your receiving room. It's dependent on the human activity that's going on there. Okay, now what this boils down to then is you've got your noisy source room, and you have determined by field investigations what the sound that is being, or noise that is being produced in that source room. And you know what you want to reduce that source room noise to in the receiving room because of the human activity that's going on in the receiving room. And you do that by constructing barriers, that is walls, ceiling, floors, etc. And that is in simplified form, that's what you're doing with noise control. Now here is a table that illustrates the use of, in the same way, of the room criterion curves, which I said in general building design is not what you're going to use. You're going to use the noise criterion curve, but this is what the room criterion curves look like. The sound pressure levels in decibels as a function of the frequency of the sound. Speech interference level is the arithmetic average of the sound power levels of the noise in the 500, 1000, and 2000 hertz bands. Speech interference level is intended to be a representation of a sound environment, noise environment that will allow two or more people in a receiving room to communicate in an appropriate manner, possibly in whispers, possibly in here is an illustration of the speech interference levels and the effect they have on the conversation that may be going on in the receiving room. As an example, if two people are 6 feet apart and you want them to be able to communicate in a normal tone of voice, then you would want to design the building so that the speech interference level or the sound level in the receiving room did not exceed 53 decibels, and so on and so forth. Again, with the at 6, if the people are 6 feet apart, they could communicate reasonably in raised voices in a 59 dB environment, and so on and so forth. This just illustrates the the concept of speech interference levels. These are so people, two or more people in the receiving room needing to communicate to each other. Now, how does the sound get from the source in the source room to the eardrum of the receiver, of the occupant in the receiving room? Well, you can think of it as the interaction of little air molecules, if you will. The source of the sound is, say, a piece of mechanical equipment, and it is vibrating, and it sets into a vibrational mode air molecules that are immediately adjacent to it. And then those air molecules set into a vibrational mode, other air molecules that are a little further away. And this keeps going on in a continuous manner until the air molecules adjacent to the barrier, to the wall, are set into the vibrational mode. And then the wall structure is set into a vibrational mode. That solid structure then impacts air molecules on the receiving room side, and the acoustic energy is transmitted from molecule to molecule until it gets over to the human ear in the receiving room and begins to vibrate against the eardrum. And that produces a sound, and the brain perceives that. So there can be a certain amount of the acoustical energy that is absorbed due to the in the source room, due to the distance between the source and the barrier or the walls. In other words, the farther away the wall is from the source, the lower will be the sound pressure that it is perceived by the wall. And there is some reduction in sound pressure level due to distance. The further that the sound source is from the barrier wall, the greater reduction there is in the sound power that impinges upon the barrier wall. There is also a certain amount of the acoustical energy that's absorbed in the source room by interaction with essentially the finished material in the source room. And in general, the finished materials, the walls, the ceiling, carpets on the floor, they reduce the sound by essentially the vibrating air molecules impinging on, say, fibers in the carpets or in the wall coverings, and those fibers deflect microscopically and absorb a certain amount of energy from the air molecules. This is a small amount that is absorbed uh, uh, by the finish materials. Generally speaking, softer materials tend to absorb more sound in a source room. With hard surfaces in a source room, there is not as much absorption taking place. And so the sound is reduced in the source room a certain amount, not very much, but a little bit, due to the distance between the source and the barrier wall, and due to the soft finish materials. And then the same thing takes place on the receiving room side. If the receiver is a long distance away from the barrier wall, there is more acoustic energy that is absorbed between the barrier wall and the receiver's ear. And also, the finished materials in the receiving room are also going to absorb a certain amount of acoustic energy. But again, this is not a large reduction that takes place. So most of the reduction of the sound that moves from the source to the receiver needs to be absorbed in the barriers, in the walls, the ceilings, and the floor. And this is where you as the building designer come into play. There are every building material has certain acoustic characteristics. In other words, some materials, like say concrete, will absorb sounds at higher frequencies or lower frequencies than some other building material. And so the building materials that you select, every building material has different acoustic characteristics at different frequencies. So you need to be aware of the frequencies that are being produced in the source room, and then select the building materials that have the highest absorption at that frequency. Let's push on here and get to some other concepts. And this is the one of the sound absorption coefficient. And this is a measure of the degree of that certain building materials will absorb sounds, and they're determined by test. You can't calculate these. These have all been determined by laboratory and field tests. An example is the typical wall between rooms. 2x4 steel studs at 16 on center with 5/8 chipboard each side. What is the sound reduction coefficient for that material? Well, this is determined by field and laboratory test. And here, let me get this slide up here. Here is an illustration, and it's not one that you can see clearly in this small screen, but when you get the slides from PDH source, you can read this better. And this type of information is also available in the technical literature and from suppliers of building materials. But you see here in this illustration, for these different types of building materials that you see here, concrete, fabrics, floors, glass, chipboard, marble, or tile, that there is a sound reduction coefficient for that given material at a given frequency. And then it has a sound absorption coefficient that is different when the frequency is different. And so you want to select your building materials that will provide you with the degree of sound reduction that you need to have to get the sound from the source room reduced to what is acceptable in the receiving room. And you get the bottom line is you get these sound transmission coefficients largely from the literature or from material suppliers. In other words, the typical dividing wall between a source room and a receiving room might be 2x4 steel studs at 16 on center with fiberglass bats between the studs and with 5/8 chipboard each side. In the commercial arena, the suppliers of building materials have, to a very large degree, gone out and had independent testing laboratories like Underwriters Laboratories field test these construction schemes and determine what the sound transmission coefficient, the single number appropriate for that wall construction system. And then you're reduced to a simple building design challenge, which you know that you want to reduce the sound, which is about, say, 70 decibels in the source room. You want to reduce that to 30 decibels in the receiving room. 70 minus 30 is 40. So you need to select a building material or building construction system that has a sound reducing coefficient of 40 decibels. 70 minus 30 equals 40. And so if you construct the wall that way, you will get that sound environment that you want in the receiving room. There are a number of things that you can do to improve the sound reducing characteristics of a barrier. One effective tool you can use with the typical stud wall construction is to put fiberglass bats in the airspace between the studs, and so the sound passes from the source through the air to the barrier wall, sets the chipboard a vibrational mode, acoustic energy. And that the chipboard then sets the steel studs into a vibrational mode on a microscopic scale. And then some of the air in a wall barrier is the sound is transmitted through the air gap between the studs. And that's where the fiberglass bats come into play, because then the air molecules with a higher level of acoustic energy, they impinge on these very light fiberglass fibers. The fibers bend and absorb energy, and so you get some sound reduction as a result of having these fiberglass bats in the airspace. And then the rest. So with a sound barrier like a wall, the sound gets through the barrier um, uh, through the solid elements in the wall construction and through the air in the wall construction. And all of these building materials and building systems through the commercial enterprise that has gone on for decades and decades and decades. A system has been developed of what's called sound transmission class. And different barrier schemes or designs have been field and laboratory tested, and using the appropriate ASTM methodology, Underwriters Laboratories or somebody like that has determined that this wall construction system should have a sound transmission class of such and such, and say 40. And so if you've got a sound source in the source room of 70 decibels, and you want to have a noise environment of 40 decibels in the receiving room, then you need to select a barrier that has been tested and has an SCT rating of 70 minus 40 or 30. Another technique for improving the sound reducing characteristics of barriers is to construct double stud walls or staggered stud walls, so that the chipboard that is attached to the stud, one set of studs, is not attached to the same set of studs that the chipboard on the receiving room side is attached to. So you've broken the sound path through the solid elements of the wall. So that is a technique that can be used to improve the sound reducing characteristics of your walls. Is staggered studs or double stud wall is even better. And the other things that can be done is flexible metal channels. Visualize your barrier wall of steel stud or wood stud construction, and you install flexible metal or plastic channels to the studs, and then you attach the chipboard to the flexible metal channels rather than directly to the studs in the wall. So again, you are breaking the sound path through the solid elements in the wall. And then, of course, the fiberglass bats are a very effective and cost-effective tool. Okay, that, let's see, gets us pretty much through what we can touch on today. Some of these tables, here's another table. These are some good tables. Transmission losses for different masonry and concrete construction walls of different thicknesses. And this table illustrates that what the sound reducing characteristics of the wall would be if it was 4 inches thick, 8 inches, 16 inches, and what the reduction would be at the different frequencies. And here is more of the same. So all building materials, essentially, you can represent by a table like this that relates the design parameters: 4 inches thick, 6 inches thick, 8 inches thick, to the sound reducing characteristics at the different frequencies. Okay, that brings us to the end of the time that we've got available. I'm flipping through these remaining slides quite rapidly, but there's some pretty good information on them. These slides here are dealing with sound propagation outdoors, and we don't have time to get into them, so I'm going to just zip through them. And now I just hang on a second. I want to just check something. Let's see. Okay, we're at the end of our time, and I know that I can't ask you to stay after class, if you will. So that's what I'm able to share with you today. Get a copy of these PowerPoints, because there's good information on them. And with that, I'm going to just thank you very much for letting me chat with you today. And now I'm going to sign off and just wish you all to have a nice rest of the day. Thanks a lot. Bye.